For problem 3, we're going to be going over radix sorts. Sort the following list using LSD radix sort with counting sort, and show the steps taken after each round. The first row is the original list, and we're going to go through this one at a time together. So this is our original list, and we know LSD works by looking at the smallest digit first. So if you just had a sort by looking at the smallest digits, what would they look like? Well, we're going to put them in like this, right? 2, 5, 5, 6. A really important thing is that our counting sort is stable, which means the relative order of equivalent items will be the same. So notice that 30395 came first in the original list and 30315 came after it in the original list. So even though they are equivalent just by looking at the lowest digit, we're going to make sure the relative order stays the same. And so this one was first and this one is second. Now we're going to move on to the next digit, and you can take a moment and think about how they'll be ordered after this. And so now looking just at the second place, we see that this item with the 1 in the tens place comes next, then the item with the 2 in the tens place. And then we have those 2 items with a 9 in the tens place. But once again, we keep their relative order. And so this item comes before this one. And the important thing about keeping the relative order is just that we don't want to undo the work we did at previous steps, right? We're sorting by the lowest order digits to get that like fine grain relative ordering, right? But we don't want to completely lose that once we start looking at the higher order digits. And so we're at this step so far. Clearly the list is not sorted yet, but we'll get there. It's time to look at the next digit. And so now this item with the 0 goes at the front, and then all these have 3s, so they go next. And once again, their relative orders are being preserved. Then we do the next digit. So all the things with 0s come first, relative orders remaining the same, and this is the 3, so it's next. And then I want you to take a moment and realize that even though this list is currently sorted, there's no way for LSD radix sort to realize that yet until it looks at this last digit, right? It has to check it, because what if, let's say this was a 5? Well, then we'd have to do one more movement here, right? It has to go at the end of the list. And LSD radix sort wouldn't know that unless it looks at that last digit. So we have to keep going, even though we're technically already sorted. LSD doesn't know that yet. And sorting by the highest digit, or this one in the 10,000s place, this is the final result. And now we have sorted all of them, and so we are done sorting our arrays. We're going to do the same thing now, but with MSD. So you can take a moment and think what happens here. Well, we're going to compare the first digits, right? And so you see that these ones all have 3s, but this one has a 4. I want you to take a moment. Is 4, so we know that in the very first round, these will all come first, remaining or keeping the same relative order, and 43092 will go at the end. Is there anything that we could possibly see in the lower order digits that could make any of these elements belong after 4 in the final result? Even if all of these were 39999 or 9999, and this was 40000, something in the 40,000s is always going to be greater than something in the 30,000s, right? So when we see this, we're done looking at this element. Now we just have to look at the remaining 3 elements, because we know the thing with the 40,000s is going to be bigger than anything in the 30,000s. In other words, the higher order digits matter more and they take more precedence. So if 4 was the only element with that higher order digit, we know where it belongs. Whereas for these, there's some ambiguity. We don't know quite yet where they belong. I also want to emphasize that if, let's say, one of these had sorted with a 1, right? Let's say this was 1. we'd also know that it belongs right there at the beginning. And so we could have filled in all of this too, right? Because it's never going to come after anything starting with 3. And so this one just happened to be the greatest thing, but it works anywhere in the array when you have this unique element and nothing else can possibly trade spots with it, right? So we know that we're only looking at these elements now because we've only seen this higher order digit, and we can't be sure quite yet what the relative ordering should be without breaking the ties using lower order digits, right? So we're going to keep looking. We look at the 1000th place, 1000th place, and we see that nothing has really, no more hints have been given. They're still all the same. We look at the 100th place, and they're still all equal. But now when we're about to look at the 10th place, think about how they're going to be ordered. Well, we know that the thing with the 1, and then the 2, and then the 9 will come first, in that order, right? 1, 2, 9. But the question is, can anything that happens in the 1's place change that? Do we have to look at the 1's place? We don't, right? Because if something has a 9 in the 10's place, no matter what belongs in the 1's place, it's definitely going to be greater than something with a 3 in the 10's place, right? Or something, and similarly, anything with a 3 in the 10's place is going to be greater than something with a 1 in the 10's place. So no matter what this value is, any of these are, we know that these are not going to change the relative positions. And so we can just skip straight to the end. And so hopefully you've seen MSD, you can actually cop out a little early, right? If you have distinct values where there's no ambiguity about where they could belong, then you can just stop right there and not do extra work. Based off this, let's recall what best and worst case time complexity for LSD and MSD radix sort. And so just as we saw in the mini lecture portion, the best case time complexity here for LSD radix sort is going to be theta Wn plus R, where W is the word length, N is the number of items, and R is the radix size. And no matter what inputs you get in LXD, you have to check every digit. Whereas for MSD, in the worst case, you have to check every digit. But in the best case, we can actually just look at the very first letter for all N elements and then move on. Just like stop, right? Because if we had the items 1, 2, 3, 200, 399, and I don't know, 501, we know that they're always going to be in this order based off the first digit, and nothing that happens in these matters, we don't even have to look at them. Whereas in the worst case, let's say you have this input, and so you look here and you go, okay, I need to look at the next digit, no ties have been broken, and you look at all of the digits, right? So that's the worst case for MSD radix sort. You can't ever cop out early because you're still unsure. And are these stable? Yes. We just saw that the counting sort has to be stable, or else you'll like mess up the work that you did in previous steps, right? We want to keep things in the same relative order. The last part of this problem asks, we just saw above that radix sort has great runtime with respect to the number of elements in the list, and that was n, right? Given this fact, should we say radix sort is hands down the best sort to use? Pause the video and consider this, and then come back. And I'm going to say radix sort is not always the best sort to use. We can't make that statement hands down, right? It is linear with respect to the number of elements, which we can never do with a comparison sort because, as we said, comparison sorts are lower bounded by n log n. But even though it's linear with respect to n, we can't say it's the best because it's not always applicable. Unfortunately, radix sorts only work when we have, we're sorting items that can be broken up into digits, break-in. When we have items that can be broken up into digits like numbers or strings or other things, and those digits come from a defined radix of like limited size, right? The other thing is that it's proportional to the radix size. So if there's like a million possible things in your radix, it's not going to work very well, right? And so that's why we can say radix sorts are not always the best to use. And that is all of this problem.